Guys, this is Niels Bohr, and essentially he studied electromagnetic spectra, color changes, and color spectra of different elements, and he made a model based off of hydrogen. And it's our first attempt to understand that the location of the electrons around the nucleus determines their energy. See, at first the thought was that the electrons orbited the nucleus like planets orbit the sun. The problem with that theory is the reason the planets can do it is the planets save energy by rotating themselves as they move around the sun. The electrons don't do that, so what would happen over time is that the electrons would lose energy and that rotation would become erratic. And therefore it would become chaotic and the atom would fall apart. So what Bohr did is he realized that when he looked at exciting the electrons in, let's say, hydrogen, that specific colors would be seen at different wavelengths. Which means that my electrons had to be able to absorb a different amount of energy, because we got to go back to our formulas that we learned. We learned that, C equals wavelength times frequency, and that energy equals H times frequency. And therefore, if we wanted to, we could say over here like frequency equals C over wavelength. So therefore, we could rewrite this one if we wanted to as E equals H times C over lambda. And this is what your book does. It combines the equations. I combined it a little bit different the last time to show you the different ways you can combine them. I like using these two separate, but if I'm having a different or seeing a different color based on, again, the electrons being excited, I must be getting different wavelengths. So here's what Bohr basically said. Bohr basically said that here's our nucleus, and he's doing all this time when Rutherford is finding out the electrons, or disproving the plum pudding model, finding that the electrons are outside, that we have a nucleus. All right, and he's saying that, we have a level here, and then we add another level, and another level, and another level. And the bigger the levels get, the more electrons we can hold. And so on. Now he calls these levels n for the level number. And he says that the one closest to the nucleus is n equals 1. Then we have n equals 2, n equals 3, and so on, all the way up until n equals infinity. Just wanted to make sure I was recording. N equals infinity. At n equals infinity, that level is no longer part of the nucleus. Now, do we ever reach that? No, absolutely not. But it's just that what was the math showing here? Now, as we move away from the nucleus, and we usually show it upward, but I mean, since it's a sphere, we can go either way. But as we move away from the nucleus, as our level goes up, our energy increases. So it requires energy to move from n equals 1 to n equals 2. It requires energy to move from n equals 2 to n equals 3. Now similar, if I'm going to move down, so I should put a plus sign here. Let's put a little plus energy there. As I move down, I'm going to lose energy. Now I'm going to lose it in the same amount. It's just one's going to be positive and one's going to be negative. And negative and positive, just like heat in our case here. Negative and positive in our case is, do I lose or do I gain energy? So in order to move up a level, I need to gain energy. How much energy? Here comes Planck's formula. And in order to move down, I'm going to lose that energy. Now here's the fun part. These electrons will absorb the outside energy from whatever source. Whatever source is going to give that outside energy. They're going to go into what we call, instead of where they start, it's known as the ground state. They're going to go into an excited state. But they don't like to be in the excited state. So they absorb the energy, they get to that excited state, and then they fall back down to the ground state, releasing that energy. Now that energy, if we look at our formula, will have a corresponding frequency. That frequency could then have a corresponding wavelength. And that wavelength might fall within 400 nanometers to 740 nanometers, and you see a specific color. This is known as the line spectra for the element. It's also the principle behind fireworks. Okay, if we were in lab, I would light stuff. I think I did. I showed you guys that, those of you who had lab with me, we lit the magnesium on fire and saw the bright white, and then I lit some copper sulfate and we saw green based on the copper. Okay, that's exactly what's happening. Electrons are getting excited by the flame, the heat source, and then they're absorbing that energy, reaching some new level, and then they're dropping down, releasing that energy. That energy has a frequency and a wavelength that essentially has a wavelength that falls on the visible light spectra. So, not to ruin fireworks for you, but I do this every 4th of July, and my wife gets ticked off at me about it and says, can't you just enjoy the fireworks? But if a purple one goes off, I'll be like, okay, that's potassium. The bright white ones are magnesium. Green is rarely copper. Sometimes it's usually bismuth. Sodium has a bright orange color. And she's like, can't you just enjoy them? Why do you have to add that to it? That is me enjoying it. Again, I am a ton of fun at parties. And now I just ruined fireworks for you to allow you to ruin fireworks. Or if you mean by ruin, make fireworks even more exciting. So, here was an interesting thought. A student and I were having a discussion the one day about how our energy has to go somewhere at the end, and when you're dead, and animals could eat you and blah blah blah, and now you could become a tree. She came up with an idea and said, what if we made ourselves, all right, the carbon base behind fireworks? And instead of having a funeral, we mixed ourselves with some metals, just like you would fireworks, and you would have a firework display instead of a viewing. And I was like, that's kind of interesting. Again, a little weird to think about, but yeah. I mean, technically you could be a firework. All right? Or a bunch of fireworks. Okay? I have no idea, Kelsey. Hey, Kate, come here a second. Kelsey just asked, if I ruin fireworks and I do all these science jokes, why did you marry me?
Because you did that after I married you.
She says I played it cool and then did it after I married her.
You played it cool. You were never cool.
I was never cool, is what I was just told. Okay. All right. So, this is the Bohr's idea of what the atom looks like. Okay. And he based it on hydrogen. Yes, I was also never cool. And she's full of garbage on that, because when I started dating her, she was still in school. And one of our dates was I was tutoring her how to do factor label method in the library. So if she says that I didn't play the nerd card right off the bat, she's full of it. But anyway, I digress. I digress. All right. Here's the issue with the Bohr model. The Bohr model works for all of our atoms, but the formula that he used only works for hydrogen because hydrogen only has one electron. The formula that he derived or utilized doesn't really work for the rest of the atoms out there. Okay? Because they have multiple electrons. All right. So what I'm going to show you, all right, only works for, only works for hydrogen. But the principle, the idea was applied to everything else. All right, so here comes the formula. Our last formula that goes with these. Okay. Energy of a transition is equal to, all right. Now this is known as, they use capital H in the book instead of lowercase. This is known as a Rydberg constant. There's multiple constants. It all depends that are called the Rydberg constant. It all depends on in what principle we're talking about here. Okay. This is all, in our case here, 2.18 times 10 to the negative 18th joules. Okay, is its value. Okay. So again, if you look it up, there's going to be different values for this depending on the units. All right. And all right, it's 1 over nf squared minus 1 over ni squared. Okay. She's also lying because we dated like 10 years before we got married. So she knew about He-Man, she knew about my science, she knew. Anyway, all right, I'm off that now. Am I though? Probably not. NF and NI are Bohr's model that we just talked about. Okay? The N levels, if you will. Okay. So, what does this exactly mean? I want to know the energy. And let's say in a hydrogen atom, the electron moved from n equals 2 to n equals 4. Okay? So I would plug into this formula. Where's my final destination? NF 4 squared minus 1 over 2 squared. We would plug this value in here and we would do the math. So, our energy would equal 2.18 times 10 to the negative 18th joules times 1/16 minus 1/4. Okay, and of course this would be a negative value. Now, I'm going from 2 to 4. I'm moving up levels. I'm absorbing energy, so my energy should be a positive value. So, let's see what we got here. 1/16 minus 4/16. So 3/16, negative 3/16 times 2.18 exponent negative 18 equals 4.09 times 10 to the negative 19th. It's a positive. That's a 19, I swear. Okay. Joules. Now, if I were moving from 4 to 2, the only thing that would change is this would be a negative value. And negative and positive are just telling me direction. Okay? Negative and positive are just telling me direction. So you'd have to be told this only uses for hydrogen, but, okay, let's say that I now wanted to know the frequency. All right, I now wanted to know the frequency, the new value. I could plug this in here and take it the next step. So I'm going to write this value down, 4.09 times 10 to the negative 19th joules. And let's say they wanted to know the frequency. All right, well, if you want to know the frequency of that energy transition, what would that frequency be? All right, then we would go here and we would say, all right, energy equals h nu. Therefore, nu equals E over h. The biggest mistake I see in the exam is people put h over E. Don't do that. So that's going to equal to the joules, 4.09 times 10 to the negative 19th. Joules. Planck's constant, 6.626 times 10 to the negative 34th. All right, let's see what our answer here is here. We'll find our frequency. Now realize this is in joule seconds, so my joules cancel out. And exponent negative 19th divided by 6.626 exponent negative 34. That looks right to me. My frequency is 6.17 times 10 to the 14th. So now we found our frequency. Our units are 1 over seconds, also known as a hertz. What if they wanted to know wavelength? If they wanted to know wavelength, we use this formula here. Okay. And we say wavelength equals c over nu. C is the speed of light constant, meters per second. Okay, our frequency we calculated, 6.17 times 10 to the 14th. So I take 3 exponent 8 divided by 6.17 exponent 14. Okay, and this is in 1 over seconds, so my seconds will cancel out. And I'm left with 4.86 times 10 to the minus 7th meters, which would be, if I do the conversion, 486 nanometers. So this transition, I know I'm absorbing, but if I went down from 4 to 2, I would release a color around 486. And that should be in the, blue region, 486 nanometers, blue, indigo, violet region. So, given our new equation, okay, in 3 steps, you can go from figuring out the energy to figuring out the frequency, okay, all in a transition. And I'll give you homework that deals with this. So our third formula that goes with this one up here and with the Planck's one there is energy is equal to the negative Rydberg value 1 over NF squared minus 1 over Ni squared. All right, questions on that? As long as you stay organized, it's plug and chug. As long as you stay organized, it's plug and chug. Okay. All right. So, what does that do for us? Well, the Bohr model, again, is only good for hydrogen. It can't do other atoms. There's too many electrons. It explains the wave properties, but we know that light can act like a wave or it can act like matter. Okay? So it can act like a wave or like a particle. So it didn't accommodate for the particle part. So what we did take away, though, again, it's good for hydrogen. What we did take away is that my electrons' energy comes from the fact that they're at distinct levels from the nucleus. And I need a certain amount of energy to move those electrons from a level to another level. That's important. You could try sample problem 7.3. You need to use your book to do it, but sample problem 7.3, try for homework. And I'll give you a couple more on that, but try it, and the answer's there. Oh, look at that. I actually did the one. Never mind. I made those numbers up, and I did that exact one. Okay? My bad. So, Bohr's model, again, had limitations. So we have to come to this other guy. Okay? Using Bohr's model, using Einstein's research, and using Planck's equation, a guy by the name of de Broglie, if you want to get really into it, his name would really be like de Broglie, like that, derived an equation that combines both, both the wave particle, the wave function of an electron and the particle part of an electron to make a wave particle equation, and we call these matter waves. So de Broglie's equation allows us, okay? And this is amazing. At least in my opinion, again, it's amazing. So de Broglie's equation is this. It says wavelength is equal to Planck's constant, okay, times mass times velocity. Okay? This is mass, and it has to be in kilograms. This is velocity, not nu. This is not frequency. This is velocity in meters per second. This is Planck's constant. This is wavelength in meters. Okay? And this is Planck's constant in joule seconds. Now, okay? I want to explain something over here. A joule is a kilogram meters squared per second squared. That's why this needs to be in kilograms, meters, and seconds. Okay? All right. So our formula again is wavelength equals Planck's constant over the mass times the velocity. Now, why is this equation important? Again, it takes the wave part of an electron, it takes the particle part. Here is the wave part. Here is the particle. Mass times velocity is known as momentum. So what? What's the big deal? Whoop-de-doo. What the big deal about this is that anything that has mass and a velocity, in theory, has a de Broglie wavelength. That means this right now. This pen or marker has mass and is moving back and forth. Okay? Me running across the screen, a car, a ball, an airplane, anything that has mass and velocity now de Broglie, yes. anything that has mass and is moving has a wavelength. Which means that you, in theory, at some velocity, could give off a wavelength where we see a color. Problem is, this works really good with electrons. When masses get bigger and bigger, the speed has to be changed. So those of you in the comics, okay, and know who the Flash is, when the Flash runs, you see red or orange or yellow. Let's say we see red when the Flash runs fast. Okay? And you could try this for homework and see how fast. So let's say the Flash is, I don't know, what do you think the Flash is? About 160 pounds-ish? So let's say the Flash is, give or take, 80 kilograms. Okay, so if something weighed 80 kilograms, and we were looking for something around 700 nanometers wavelength, what would the velocity have to be? What would the velocity in meters per second? Figure it out. You're going to be disappointed. You're going to be disappointed in it because the Flash doesn't actually have to move that fast. Due to its high mass, it needs a lower velocity. Okay. So electrons have a low mass. They're going to move fast to give that wavelength. The bigger the mass gets, the slower the velocity has to be to see that color. So try that one for homework and see what you get, how fast. Is that official? Every time I bring that up, Rob, in a class, I wait for the biggest, like, Flash nerd or whatever to jump in and say 195 pounds. If that's official, I don't see how he's 6 foot, but, you know. But if we say, okay, 195 pounds, 2.205. Okay, he's 88 kilograms then. Exactly, that's what I'm saying. Is that canon? All right, let's change it to 88 kilograms to be official here. See how fast they have to move. The thing is, you have to remember, if we go back to de Broglie's equation here, an electron's mass is times 10 to the negative, 28th. So the velocity is going to be super fast to get this wavelength. If I increase the mass, according to fandom, did you seriously look that up while I was talking? Like instantly had to know what the Flash weighs? Okay. So calculate that. See how fast the Flash has to run. It's not fast at all to have that red or yellowish orange color behind him. Okay. But importance of this equation is the fact that it now takes both factors of light, the wave and the particle, the wave function of light, the electron function of light, and puts them all in nice. And speaking of the cat, we're going to talk about killing the cat in a second. In one formula. Okay? All right. You could try this one for homework too, 7.4. 7.4 gives you the speed, the mass, okay? It gives you the mass in kilograms, all right? I was talking in grams before, and it gives you H, so you can find the mass also. Just make sure your units are correct, guys. Okay. So based on de Broglie's work, we get new techniques like X-ray diffraction because we understand what's going on with the electrons and their movement and all of that, and the wave properties and electron microscopy, so we could start looking at smaller things. X-ray diffraction and things like that is how we discovered the double helix. Not we, I wasn't there, but how Rosalind Franklin was doing X-ray diffraction and basically saw the double helix of DNA. So the discovery of these wave properties of matter, meaning anything that's moving has these wave properties, led Werner Heisenberg to come up with the Heisenberg uncertainty principle. Now, what this means is, okay, I can't know the location and the speed of an electron at the same time. I can know one without knowing the other. Okay? If I measure the speed of the electron at point A, that electron's already gone. So I know its speed, but it's no longer in that location. If I pinpoint it and stop it and pinpoint that location, I don't know its speed anymore because I've stopped it down to nothing. And that's like a really simple explanation just to kind of wrap your head around it. It's not totally 100% correct. But the way I always explain it is, if you were standing at the side of a road and you had a radar detector and you were measuring a car going by, you might be able to measure that car's speed, but you have no idea where that car is now. Because the way it measures is the radar goes out, then bounces back. That car is no longer at that location, but you know its speed. If you were to stop the car and pinpoint its location, you no longer know its speed because it's not moving because you pinpointed the location, so you can't measure its speed. Again, simplifying it, not 100% accurate, but just to get the idea. So what I can do, though, using this idea is I can measure the car's speed and I could generally know where the direction is. I could generally guess the probability of where my car would be if I'm standing at the edge of the road. But I can't know the exact position and the exact speed at the same time. So Schrodinger comes up with, and we're not going to do the calculus and the stuff behind it here, or worry about wave functions and psi squared and all of that. But what Schrodinger basically comes up with is a mathematical expression that takes both the wave and particle of the electron, okay, takes those species, and basically says that where my electron is sitting, here's the probability of where I would find it, and since this is the probability, I could kind of figure out what shape my electron is essentially sitting in. So here's the deal. With Bohr's model, okay, all from Bohr's model, we know that the electron's energy comes from where they are sitting. What we didn't know, and this is where the math took us further and Schrodinger finishes it off, is that not only is it the level that they're sitting in, but they also have little tiny compartments that they're sitting in that we call orbitals. Okay. So Schrodinger came up with, to simplify all of this, and we'll talk about this in a second, Schrodinger comes up to simplify all of this with a story or an experiment of something called Schrodinger's cat, to explain this Heisenberg uncertainty principle that you can't know two things at once, and once you observe the other is canceled out. So once I observe the electron speed, the location's canceled out. Once I observe the location, the speed is canceled out. Now, and if I don't observe them, they both have location and speed. So I know my electrons are moving, and I know they're in a specific location. But once I look and find its speed, the location is gone. That's not a choice anymore. So what Schrodinger's cat was, you put a cat in a box with a vial filled with poison that'll kill the cat when the vial opens. Okay? Now, when you seal the box at time 0 with the cat and the vial in there, that vial could instantly break, or that vial could take 3 years to break, or 3 seconds, or 30 minutes, or an hour, or 5 days. So at time 0, we seal the cat up with the vial in the box. Is the cat at time 1 second alive or dead? Well, without observing the box, without looking in the box, without doing anything, we have to assume that the cat is both dead and alive. Because we don't know if that vial exploded or not. Now, we open up the box, the vial is intact, the cat's alive, fantastic. That cancels out the dead cat probability. We open up the box, the vial exploded, the cat's dead, that cancels out that the cat's alive. But until we observe it, we have to assume that that cat is dead and alive in the box at the same time. The same thing with the electrons. Until we observe them, we assume that they are moving and have a location at the same time. They have a speed, they have a location. So that leads us to our second joke. If you've been listening the last couple minutes, you'll get it. If not, too bad, listen to the video again. Heisenberg and Schrodinger are driving in a car. Heisenberg's the driver, Schrodinger's the passenger. A cop pulls Heisenberg over, walks up to the window, and says, "Excuse me, do you know how fast you are going?" Heisenberg looks at the cop and says, "No, I don't know my speed, but I know my location." The cop looks at him and says, "I don't like that answer. I need to search your car." He says, "Pop the trunk." The cop walks back to the trunk and says, "Hey, do you know you have a dead cat back here in the trunk?" And Schrodinger says, "I do now." Ba-dum boom ching. "I will be here all week. Please tip your waitresses." Again, if your friends get the joke, keep them. If they don't, you need new friends. Okay. So, what Schrodinger's mathematical equations allow us is something called probability density. And this is essentially what an electron would look like or where it would be. She's playing fast and loose because she knows what her grade is right now. She knows she could screw up the final and still do all right. Okay? Electron density is, and again, all right, where am I most likely to find an electron? I want to point out it's an XYZ coordinate, which means that these orbitals, these holders for the electrons, are in 3D shape. Okay. And that's going to lead us to something called quantum numbers. Okay? They're really letters, but they're called quantum numbers. Now just bear with me here. Okay? It'll make sense in a second, I hope. All right. Here's the example I use to explain quantum numbers. Instead of drawing an atom out and worrying about an atom, okay, and saying, okay, there's different levels of the atom, let's all use something that we are familiar with. All right, we are the proud owners of Hotel Atom. Right, Hotel Adam is near Club Beaker, so after a long night at Club Beaker, you can get a room at Hotel Adam. All right. We've got the lobby down here in Hotel Adam. And the lobby is going to be equivalent to our nucleus. Now, of course, the atom is spherical in shape, and we're looking at it in this sense, but it's the same thing that we're going to look at. Okay? Nucleus. Okay. So, what do we need to be a successful hotel? The first thing we need is floors. Okay. We need floors. So we're going to draw in 4 floors. Then we need rooms. Draw a room in here. Okay. It's a little too big. I gotta extend Hotel Adam out here. I need a little bit more room. Alright. We need one more long one there. Okay. Let's make this one a little bit shorter and that one a little bit longer. That'll work. Okay, we need rooms. And then we need divisions in our rooms. We'll have fancy rooms, we'll have plain old rooms. Okay. Okay. All right, there's our hotel. Now the floors are really our first quantum number, which is known as n, and it deals with Bohr's n value. So, in our atom, this would be n equals 1, n equals 2, n equals 3, and n equals 4. Okay? Just like the model we talked about at the beginning of the lecture. Now, the type of room and number of rooms I have on each floor. And I know what you're thinking. Well, you only have one room on the floor. Yes. Okay, I do only have one room on my floor. The thing about that is, the rooms are based off of, okay, the rooms are based off of what n is. And the rooms are letter L. Okay? So that's our second quantum number, which is a letter. Okay. Now, n is known as our electron shell. L is known as our electron subshell. And the way we calculate it, okay, is 0 to n minus 1. Okay. So, it's all the positive integers between 0 and n minus 1, including 0. So on floor 1, it would just be 0. On floor 2, 0, and 2 minus 1. Okay? On floor 3, it would be 0 up to 3 minus 1. So 0, 1, and 2. N equals 4. 0, and then 4, n minus 1 is 3. So 0, 1, 2, and 3. Okay? Now, there's code for this. If my value is 0, we call it S. If it's 1, we call it P. If it's 2, we call it D. And if it's 3, we call it F. Okay? So on floor 1, n equals 1. Our L value, our room number, goes from 0 to n minus 1. 0 to 0. This would be known as a 1s. On floor 2, okay, what's our values going to be? 0 and 2 minus 1, so a 0 and a 1. Here's our 0, which is equal to 2s. Here's our 1, which is equal to 2p. And then so on and so forth. This is going to be our 0, which is going to be 3s, 3p, 3d, because 0 to n minus 1. N minus 1 is 2. All the integers, 0, 1, and 2. 4s, 4p, 4d, 4f. All right. Anybody lost where I got the numbers or what's going on here? If not, then our next quantum number, okay, deals with the number of divisions. Deals with the divisions, okay? Deals with the room breakdown. Okay, so we're going to say divisions. Okay, we call these the orbitals. And they go from negative L to positive L. That's a cursive L. And the letter that represents it's M sub whatever the L we're talking about. Okay. So this one is based off our L value. So in S, we have only one division. Okay. In P, P's value is 1. So our 3... Negative 1, 0, positive 1. Negative 1, 0, positive 1. These are all 0, 0, 0. Every S, every P will be negative 1, 0, and positive 1. Negative 1, 0, and positive 1. -2, -1, 0, 1, and 2. For D, D is 2. -2 to +2. -2, -1, 0, 1, 2. How about F? F is 3. -3, -2, -1, 0, 1, 2, and 3. Which means, okay, and then here's the thing. Each orbital can hold 2 electrons. So level 1 can hold 2. Level 2 can hold 2, 4, 6, 8. Level 3 can hold 2, 4, 6, 8, 10, 12, 14, 16, 18. Level 4 can hold 18, 20, 22, 24, 26, 28, 30, 32 electrons total. So this is why as we get further away, we get more energy. Okay? Questions on this? So those are 3 of the 4 quantum numbers. We'll talk about the 4th one in a second. Okay. Nothing? Are we sure? So what this means is that we can hold a different amount of electrons on each level. Okay? There's one more quantum number out there, and it's known as ms. And ms is just spin of an electron, how an electron's spinning. And the 4th quantum number, ms, the only options are +0.5 and -0.5. Okay? Now, here's the deal. We've got 4 quantum numbers. We got n telling us the electron shell. We've got L telling us the subshell. And it goes from 0 to n-1. So it's based on our n value. We've got M sub L, which is known as our orbitals, which goes from -L to +L and all integers in between. Whole number integers in between, and these can hold 2 electrons each. And then we have the spin, ms, which is +0.5 and -0.5, or -0.5. Now, the thing about this is there's something called the Pauli exclusion principle, and we can't have the same 4 numbers, and this is in the slides, further down in the slides, all right? But we can't have the same 4 quantum numbers for an electron. Each electron has to have its own set of 4 quantum numbers. So, how do we utilize these? Well, it depends on how specific you want to be. Okay? So, let me give you examples here. All right? I tell you that there is an electron located in the 2n. Okay? 2 equals n subshell. Or electron shell, I should say. And I want to know what are the quantum numbers. Okay? For this electron. So this is the most general one. It'd be like me saying, okay, the student we're looking for is in building 4 at LCCC. Well, where could the student be? The student could be in any of the bathrooms, any of the classrooms, any of the labs, any of the offices. So we'd have to list every location. 408, 409, 412, 413, and so on. So that's what we have to do here. If n equals 2, the electron could be on an L level of 0 or 1. Okay? Because we go from 0 to n minus 1. It's m sub L. Well, I need an m sub L, so this is S, don't forget, and this is P. I need 1 for S, and I need 1 for P. Okay. And I know it should be M, P and all of that, but we'll put the L in there. Okay, for S, if it was sitting in the S, it'd be sitting in the 0 orbital. So I'd be on electron floor 2, shell 2. I'd be in subshell S, and I'd be in orbital 0. What if I was in the P shell? Well, then it'd be -1, 0, or +1. And what would its spin be? Well, its spin could either be +0.5 or -0.5. And there's all of its possibilities. Okay. So let's expand it a little bit. Let's take it a step further. And let's get more exact. Now the electron is in the 2p. Okay, we're going to get a little bit more specific. We're going to be in the 2p. All right, its n value is still the same. It's still on level 2. Now its L value, we know it's in the p. All right, so this is giving us the n value. This is giving us our L value. I know it's in the p, so this definitely has to be a 1. Okay, or the p, if you will. Where is it in the p? Well, I'm not sure. I just know it's there. So it could be in -1, 0, or +1. What's its spin? Not sure. Could be +0.5 or -0.5. Either one will work for us. Then we get even more specific. Okay? Let's say we literally, now your book uses boxes to draw out the orbitals. I'm going to use lines, because you can also use lines. Let's say the electron is sitting here. A half arrow up or down represents, all right, an electron. A half arrow like that, up or down, is the representation of an electron. So let's say we're talking about this specific electron here. All right, we have its n value. We have its L value. Here's the -1, 0, and +1 of the m sub L. So if I want to know that electron specifically, n equals 2, L equals 1 because we're in the p, and my m sub L, now I know specifically this student is in 411 sitting at this desk. I know it's in the -1. And its spin, if you want to call up positive, +1/2. Okay. Now, what about that whole we can't have the same 4 quantum numbers thing? Okay. What if I had this electron here sitting next to it? Okay? And I want to know its quantum numbers. Well, it's still in level 2. It's still in a p, so it's still 1. It's still sitting in the -1, so there's 3 that all match up. The fourth one has to be different. So that's why we have to write a -1/2, and that's why I drew it upside down. So the question is, which one are they asking you for? Do they want you to be uber specific? Or are they just giving you list all the quantum numbers for a general shell level? Okay, questions on this? Because this is where I want to end today, guys. So please, if you're confused by any of this, let's go over it. If not, all right, then let me give you some homework. Let's get some homework that deals with what we covered today. All right. Page 325. Seven point 20. 7.2324, plus the slide problems that I talked about during the lecture here. 7.29 and 30. Seven 7.39 to 7.42. Don't worry about uncertainty. In 739 and 740, they ask about uncertainty. Don't worry about that. And with this orbital stuff, 7.49 to 7.52. 7.55 to 7.60. Okay. Also, your final. I know I posted the schedule online for you there, but just a reminder, your final on just whatever we cover, which is just going to be this presentation, will be Tuesday, May 12th. Same format. All right. 12:30, right? 12:30 to 2:30. Yep. 12:30 to 2:30. It'll be accessible from 12:30 to about 20 to 1. I have to give it at that time. We were told we have to give our finals at the scheduled final time. Okay.